In this 8th lecture, we're talking about legged robotics systems, and in the first part, in the first video segment, I would like to give you a very brief introduction to what legged systems are, why we're building them, and also some glimpse about the history of legged robotics. The reason we're building legged systems is simply because they have the potential of being much more mobile than any legged or tracked vehicle that we can see today. Here's a couple of examples of situation where you can see how legged systems can profit. First thing is, if there is a gap, you can simply step over it. Same for a step. For all of that, you need very complex suspension systems with a wheeled vehicle. Then for ramps, this is primarily because you can shift the center of gravity with respect to the contact points, which allow you to remain stable even if it's very inclined. Once you're falling, there is no chance of getting up and continue to operate with a wheeled vehicle, while you can simply do this with legged systems, and you have very discrete footholds that allow you to selectively step on things or avoid things. The fact that it's very mobile comes at certain costs, and these costs are that it's extremely hard to control the systems, and you have many degrees of freedom that you have to coordinate in order to move the system, and the system has to interact with uncertain environments, so it has to also have a very detailed knowledge about its environment. The dream of building legged systems goes back very, very far. Here's a couple of first patents that were made for like mechanical horses, so horses that are driven through gears and cranks and levers that interact in a manner that you can turn one crank and the system simply moves as a horse would be moving. And the nice thing is that these mechanisms that were developed at the time, or these ideas behind that, they were even included in some of the first machines that were really walking and that had an engine to propel them forward. These mechanisms find still application today. What you see here are the strandbeest developed by Theo Jansen, who is a Dutch artist and sculptor. So this is a mechanism that walk as if they would have legs, propelled simply by the wind. So these are mechanisms that are connected purely mechanically throughout the huge machine, and when you move them in one or the other side, these crank mechanisms, this makes motions like leg motions of a human or an animal and make the system move like that. This is purely passively. Really the only energy that is added to the system is coming from the wind. And that also shows you a little bit in how efficient machines can become. So walking from A to B on flat ground is in essence a zero energy work. All what they have to do is we have to compensate for the impact losses and friction losses that we have in the mechanism. But as you can see here, this can be done pretty efficiently. Similar mechanisms were then integrated in the first walking trucks. So you see here some of the machines that were built in the 50s and in the 60s and later on also in the 80s. So vehicles that are pretty heavy, as the name says, like a truck, but that have legs instead of wheels. But these legs are to a large extent moving due to coupled mechanism. At the time they didn't have computers that were able to calculate all these motion trajectories, but instead they mechanically realized that. And instead of me telling you more about that, I have here a small video by the guy who developed this adaptive suspension vehicle, and he's telling you a little bit what they were doing.
The military has been interested in legged locomotion for quite some time, at least 20 years actively that I know of. The reason is that 50% of the dry land mass of the world is impassable to wheeled or tracked vehicles of any military design.
Enter the Adaptive Suspension Vehicle, a six-legged juggernaut developed at Ohio State University for the United States Department of Defense. Ultimately, production versions of this prototype will carry men and equipment through dense forest, marshes, and boulder-strewn hillsides where even tanks cannot go. As we'll see, the work going on around the world is producing a new generation of walking robots that embody many principles of biology-based engineering. A machine with 6 legs, like the adaptive suspension vehicle, can move faster. It has 2 tripods, and this means half the legs can move forward with each stride. It actually moves its legs like an insect in a pattern called the alternating tripod. At any one time, the insect is in contact with the ground through 2 legs on one side and 1 on the other, while moving the other 3 legs forward.
A different direction are the developments by GE, which also happened around the 60s. In this example, you see the GE walking truck. This is a vehicle that has no mechanical coupling in the legs in order to make the leg move along a predefined swing leg trajectory. Instead, they have hydraulic pistons in multiple degrees of freedoms of the leg, and then they have an operator sitting in the machine who coordinates the action of the individual joints, who's opening and closing every single valve of this machine in order to make the system move around. You can see here in this video that it doesn't look very stable, and in fact it also looks physically not very correct. And that's in fact true. So the machine was hung up from the ceiling, otherwise it would just have fallen over. Simply because of this coordinate activity to move individual legs to stabilize the vehicle was that challenging for the human pilot that it couldn't be done without any like controller help, without any computer help. Back then, people didn't have servo hydraulics, so they had to. The work was very exhaustive to open and close these individual valves, and there is some reports about this GE walking truck saying that the operators had to be exchanged every couple of minutes since they were so exhausted from their operations. What I find very interesting is that this concept of having individual actuators in many degrees of freedom still finds application in some of today's construction machines without any human help. An operator sits in these vehicles and he has to open and close every single of these valves. These are in total about 25 degrees of freedom that need to be coordinated to make the system move in challenging environments. So it's very similar to this GE walking truck from a controls perspective. Big difference is now we have servo hydraulics, so it's not that exhaustive anymore. Nonetheless, it requires a huge coordination activity by the operator, and you need a lot of training to be able to operate such machines. However, once you're able to operate it, you have really like machines that can go to the most challenging environments that we're operating, but of course only human steered, not really in an autonomous fashion. If you're interested in more stories, go and check out the homepage of the Cybernetics Zoo. There's a lot of fun facts and early machines that have been developed. Among others, you will find, for example, the Phony Pony, which was the first quadrupedal system that was kind of computer controlled, so no humans had to coordinate individual legs. You'll find the Hardyman robot or exoskeleton, which was one of the first exoskeletons. You will see steam-actuated humans, mechanical elephants, and a lot more. The big breakthrough in modern electrorobotic systems was done in the 80s by Mark Raybert at MIT and at the CMU in the Leg Lab, where they developed the first dynamically balancing legged systems. You see here examples of some of the hoppers like single-legged hoppers that were stabilized through a computer that figured out where to step, when to step in order to maintain balance. They were not only building single-legged systems, but as you can see here also multi-legged systems, bipedal systems, quadrupedal systems, and the control algorithms that were propelling and stabilizing these different legged systems, they were all more or less the same. And as you can see, already back then in the 80s, these machines did crazy dynamic maneuvers and they were actually extremely advanced. The work and the research that was done back then and the people that contributed to this is also the origin of a lot of the famous laboratories and companies that are out there today. I put here just a couple of names of people that contributed to these works. In the 2000s, we then had a lot of activities in legged systems in Japan with the humanoid robotic systems that came up. Here is Honda Ashimo, also world famous, probably one of the most advanced humanoids back then. There were a series of humanoid robots developed by Honda. There was not really an application in mind with these machines, but it was more to show what can technology do, how advanced these companies are, and if there is a Honda robot, of course, there must be also their competitors' robots. Also, Toyota developed humanoid robots. These machines, they had typically many degrees of freedom. We're talking here in the range of like 80 degrees of freedom, versatile fingers, trying to replicate a lot of the morphology that we see in humans. They were mostly used for shows, for stage activities. You see here on the left hand side the robot who will walk up a stair. All of that very carefully pre-planned, kinematic planning, kinematic execution. You need to position this robot pretty precise in front of the stairs, and it cannot really deal very well with uncertainties. On the right hand side you see a robot playing a trumpet. Also there, coordinative activity of the fingers, of the motion of the system, and so on and so forth. In 2011, there was the Fukushima disaster after the earthquake. The tsunami hit very hard and destroyed some of the reactor buildings close to the seaside. We had a huge contamination of a large area. And Japan, one of the leading countries in robotics, realized that they had a lot of robots, but actually almost no solution at all that could go in these reactor buildings or into this area and provide the necessary help. They could do stage shows, they could play the trumpet, they could do many fancy things, but as it looked like, critical people said they can't really do something useful. In fact, the robots that were actually used in here were at the beginning drones to observe the situations. Later on, there were a couple of tracked vehicles that were sent into these buildings. But even now, 10 years later, there is ongoing but still very slow development in robotic solutions that help in mitigating this disaster. Inspired by this problem, DARPA launched then in 2012 the DARPA Robotics Challenge, which had the target to develop or streamline the research that is done in humanoid robotics towards systems that can possibly help in such a disaster scenario. What they have to do is they have to fulfill a couple of tasks which are related to what would have been done at Fukushima. They have to approach such a building, they have to enter doors, they have to get across obstacles, take tools, operate something with the tools, open and close valves, do stairs. but all in a relatively constrained environment. Of course, never that challenging what you will face in a real world disaster scenario, but still showcasing some of the capability. Now, where did this go? I have here a small video by the DARPA program manager back then who explains you what the challenges are and why we are not better than what we are.
The reality of robots today is very different than what we see in science fiction and in the movies in particular. The problem is that robots are really, really stupid, okay? They have very small brains, only a small fraction of 1% of the size of our brains. That's how you really need to think about them. So you have this mechanism, this machine that looks perhaps like a person, that seems to be able to move perhaps like a person, but the truth is it has hardly any brains at all. The head is empty. With a human one-year-old, you have this dichotomy. You have a very large brain inside of a one-year-old that sort of doesn't know very much yet. And so what you see is tremendous memory, you see tremendous understanding of social cues, of language, things like that. Even though a one-year-old can't speak, they can usually understand what we say. In that way, our robots don't come anywhere close to the intelligence of a one-year-old. Where our robots are similar to a one-year-old is in their competence at locomotion and manipulation. When a one-year-old tries to walk up and down ramps or up and down steps, they often fall. And it turns out that our robots have about the same level of competence right now, going up and down steps and ramps roughly that same size. They fall roughly just as often. The first challenge all the teams face is reliability. They've only had 6 to 9 months to build their robots, to begin to write software for them, to try to make them work. For the teams bringing their own hardware, that's the #1 issue. For the teams using the Boston Dynamics hardware, they have to deal with reliability of software, and that's no easy task either. So I think the hardest task that they have is making sure that all the bugs in their systems, hardware bugs, software bugs, won't end up losing them points in the challenge. Even a year from now, robots will not be able to leap mountains in a single bound. Robots will still move around relatively slowly. They will still fall on occasion. They will still need human supervision. Again, perhaps the robots will have brains that are roughly comparable to, I don't know, somewhere between an ant and a mouse, okay? They'll still be really, really dumb compared to human beings. They're still gonna need human beings to tell them which particular tasks to do. They won't be able to figure it out. But we think that for disaster response, where we do have human beings, but they have to work at a distance from the robots to stay out of harm's way, we think that that pairing, that collaborative working relationship can be quite effective. A year from now, we actually want a demonstration that will show some utility for disaster scenarios.
The competition was a great success. You see here the final winner, the DRC Hubo team from Korea. And you show what they had, this video shows what they had to do. They had to first drive with the car to the entrance. Then they had to go into a building, opening a door, and then operate a couple of tools in there, get across obstacles, and so on and so forth. But this video also shows you the challenge of it. First of all, it's sped up massively, so everything is extremely slow. And second thing is, obviously, it was still very complex to walk because the robot, it went on its knee, it had wheels on the knee, and it was driving most of the distance. And also, if you look at the most seen video on YouTube about the DARPA Robotics Challenge, you will see a lot of failures in how these robots were collapsing while stepping across relatively simple terrain, while driving through the sand, while interacting with the door. And most of these failure cases that we have seen here were primarily due to the fact that they made contact with the environment if they did not want to, or the other way around. They didn't make contact, they thought they made contact, and then they wanted to apply force to the environment and fell over. So this is absolutely not to say that the research these people were doing is not excellent, but it shows you the complexity of the problems that we are dealing here with. And I think it's still today, it's unsolved problems. A lot of the research there's a lot of research that needs to be done to make these machines being able to operate in such environments and to fulfill such challenging tasks. Since then, a lot of research has happened. I don't have the time to give you a very in-depth analysis of the current state of the art. There was a lot of work in humanoid robotics, in multi-legged systems like quadrupedal robots, in walking and driving system. Instead of giving you the overview here, I hope that I could motivate many of you to take some research projects in that field, select the corresponding labs here at ETH, follow conferences and workshops that are, in the meanwhile, a lot of them online all around the world. And I think you will find a lot of excitement around these types of vehicles. With this, we're closing this small video segment and we're diving into more specific actuation and control technologies that are required in order to make these systems move.